Hi. Previous video, the video got this thing stopped in between. There was some issue, but I was able to show you in the previous video is that the electron behaves like as electron behaves like a wave, and the light behaves like a particle. So electron has a wavelength, and I already showed that to you guys in the de Broglie equation. See, this is the wavelength of the electron. Okay, and hope you guys will by heart this equation. Now we will do some question, try to do some question banks questions over here, okay, just to get an idea how does this wave particle duality concept work, okay, how to best answer them. It's mostly repetitive words only if you notice the mark scheme, okay, but they ask the questions in various manner here and there, but you have to just know, okay, I'm supposed to write these particular important points, okay, it should make sense. Now in let's say this is one of the question that came in the question bank, okay. In 1921, Albert Einstein won the Nobel Prize for his work on the photoelectric effect. The results of this experiment on photoelectric effect shows that, so he won, actually not, we all think that maybe he won the prize for his this what relativistic theories, okay, but no, theory of relativity, not for that. He actually won it for photoelectric effect, okay. And these are some experiments they found out that photoelectrons are not released. Basically they are talking about electrons. Photoelectrons are not released when incident radiation is below certain threshold frequency. So we know this, and the kinetic energy of the electron release depends on the frequency of the incident light and not the intensity. And how does, and they're asking, explain how these results support the particle theory and not the wave theory. So we are going to learn about particle and wave theory over here, okay. The first thing we need to learn about particle theory is, so what is particle theory? Which is true, this is true, this is observed, whatever we will going to read right now is going to be observed. And wave theory is false, it's not observed, okay. Remember that it's just theory, it is not observed, okay. So first thing you should know is the energy is directly proportional to the frequency, okay. In particle theory, energy is directly proportional to the frequency, okay. Particles, okay, increased F means more energy of the photons, okay. You have to know what you guys even have to write what is the definition of photon, okay. They are packets of energy, okay. Then release of electron requires minimum energy, we call it work function. That's what they're trying to explain, the first one, okay. So if you have less frequency, you have less energy, so if you cannot meet the minimum energy, the electron will not get ejected. That's what this line is trying to say. One photon will release only one electron. Greater energy photon means it will have greater kinetic energy. That's what they said, na. If the photon's energy is less, the electron will have less kinetic energy, so it is limited always, okay. If it has more frequency, the energy of the emitted electron is kinetic energy of the emitted electron is also going to be more, okay. So that's what this kinetic energy of the photoelectron release depends on the frequency. So if your frequency is more, the energy of the photon is more. When energy of the photon is more, since one interaction is allowed, the electron which is emitting will have more kinetic energy as well. If you give more intense light, that means more photons, therefore more electrons. This is particle theory. Now, what does the wave theory used to say? Wave theory says that the energy depends on the intensity, which is not observed, of course. So, more intense light should emit an electron with greater kinetic energy. Okay, energy spread over the whole wave. To be honest, I don't know meaning of this right now. Okay, energy is spread over whole wave. Okay, right now I have no idea. Okay, if exposed for long enough, photons eventually released. So that's what I explained in my previous video, is that in wave theory, if you increase the intensity, according to them, if you increase the intensity, the electron will eventually get released, okay. Doesn't matter whether your light is having minimum frequency or not, as long as the intensity is high, okay. But this all does not happen. So you guys should know what is particle theory, you guys should know what is wave theory. Let me see if there are other such questions are there or not, okay. Okay, this is another thing they wrote. These are some answers we are supposed to know. Okay, whereas wave could build up. Okay, again another wave and oh, okay. Let me read this question for you all. So in a demonstration, Ultraviolet light is incident on zinc and electrons are emitted. Ultraviolet lights are incident on zinc and electrons are emitted. The intensity of the ultraviolet light is increased. So if you increase the intensity, you should know that the more electron gets released. Why? Because more photons and one interaction is allowed. Always write these 3 points. More intensity means more photons. Okay, the energy is same. Energy, it does not get different. Energy is same. More intensity of light, more photons. Since one interaction is allowed, since only one interaction happens between one photon and one electron, therefore more electrons gets released. See, they wrote that the number of electron emitted per second increases. Why? I just said you the reason. And the maximum kinetic energy does not change because the intensity, because the energy depends on frequency, not the intensity. They wrote that photons, mention of photons, okay, not photoelectrons. They are not photoelectrons. We call it photons. One to one relationship between photon and electron. Intensity of light relate to number of photons per second. So number of photons arriving and hitting the electron per second. Okay, frequency stays constant, therefore energy is also constant. Why? Because photon energy depends on the frequency, E is equal to hf, and therefore the energy is constant if you come to with this formula. How many marks? 4 marks. So 1 2 3 4 6 mark is there. 4 already we have written. Okay, now in next one, now let's go to the second equation. It's a second question, that is the B part of the same question. Okay, it's a star, that means you have to write it very carefully. Okay, they said explain why the following observation may be understood using a photon model. Basically, they are talking about the wave photon model light rather than the wave model. They are talking about the particle model of it, particle theory rather than the wave theory. So they said the light above certain frequency causes the emission of electron from the surface of the metal. This emission occurs instantaneously. Okay, light below a certain frequency will not result in the emission of electron however long it illuminates the surface. Okay, the answer is almost the same what we did before. Okay, it's just that some twisting of words, that's it. The first thing you have to talk about single photon and single electron interaction, always, that's a thing. Okay, and you have to talk about that the photon energy depends on the frequency. So that's first one. They above certain frequency the electron gets emitted and the emission occurs instantly. Why? Because they have energy more than the work function, and energy of the photon depends on the frequency, which is E is equal to hf. If photon energy is greater than work function, electron is getting emitted. First answer. Then whereas what happens in wave theory, whereas wave energy, if you talk about wave theory, energy could build up. Okay, electron can absorb energy continuously or over time. Okay, so any frequency should work in that case. I told you now, in wave theory the concept of threshold frequency is not there. Okay, so but this build-up does not happen. Why? In wave theory you talk about only intensity, but you know intensity does not increase the energy of the electron. Intensity just increases the number of electron ejecting or emitting from the metal surface. So try to read this question, try to read this answer and frame it up. Okay, let's see if there are other questions over here. These I haven't done these questions yet with you all. Okay, these questions, some of these questions you can revise it on your own. I think I already did enough wave theory and particle theory with you. Okay, let's see this one now. Cathode ray. Okay, cathode ray were discovered in 1876. In 1897 they said, okay, J.J. Thomson showed that these rays were made up of individual particles. These becomes known as electron. In 1927 Aberdeen University diffraction was observed when a beam of electron was passed through a thin metal film. Okay, use this information to discuss how scientific ideas develop. Very unique question. Experimental details are not required. Okay, so now before we used to consider cathode rays to be waves. Okay, Thomson showed them to be particles, and what did Thomson do? He showed them these are actually particles. The idea that the diffraction occurs for waves. Okay, so we know that the diffraction only occurs for waves. Therefore, since electron is diffracting, it is a wave in nature. That means it has a it has a this thing, it behaves like a wave also, when it's a wave as well, the electron. So electron shows wave particle duality. Okay, and how does an idea behave, changes? You have to say, this demonstrate how ideas changes in the light of new evidence, experiments or observation. So if you keep on doing experiments, you will find new stuffs, and your previous idea may be wrong, and you will adopt the new idea. Okay, I'll fewer electrons are emitted. Just revise these questions, read the mark scheme, they're almost the same. Okay, now next I'm going to copy paste some pictures, book from the Hodder, and I'll try my best to explain you guys, not next video, in this video itself. Okay, this thing, what do you call this, energy levels. I'm going to explain energy level to you guys. Okay, so this is the page I was talking about. This is from Hodder. Okay, it's page number 180, from Hodder. Okay, so now I'm going to teach you guys regarding energy level diagrams. Okay, I'm going to teach you guys regarding energy level diagrams. So these are the energy level diagrams. Okay, so here it's like different orbits in an atom. This is like a different orbits in an atom, and these energy level diagrams are actually different for different atoms. Okay, so let's say this is for hydrogen. Okay, and if you talk about, let's say, oxygen, it might be something, it might look a bit different like this. My first twos are very closer. Okay, it will look different. I may not be correct on this. So it, for, let's say, for calcium or whatever it is, it might be like this, you see, they look completely different from each other. Each level is different from other. Let's say this is for oxygen, this is for calcium, you see, and this one is for hydrogen. Okay, so these are energy level diagrams. Okay, I'll try my best to explain this. Okay, and these by seeing these energy level diagrams, you have to do some calculation. Like, one thing you are supposed to know, that the lowest energy level is known as ground state. This is known as, this particular line, the lowest line is known as a ground state. Okay, and this is, and here this is ionization. Like, basically, if an electron which exists over here, let's say, if an electron which exists over here, if it wants to escape the atom, okay, if it wants to escape the atom, it should gain energy of around minus 13.6 electrovolt. It should get energy of around minus 13.6 electrovolt. You should know this. Okay, why? Because this is 13.6 and here it is 0. Below this it's all negative. Can you see the values are all negative? And this is known as ground state. Energy is most stable over here. Okay, the most, if they tell you mark a line where the energy is most stable, you write n is equal to 1. Okay, or you just write here, mark x. This is where the electron is most stable. When electron gets energy, they go to higher energy levels. Okay, these are energy levels. This is what we call energy levels. And as I said, these energy levels are different for different atoms. For oxygen it might look like this, for calcium it might look like that. Okay, so this is known as ground state. And if an electron gains energy, it goes to higher energy levels. When an electron gains energy, it goes to higher energy levels. And it might go from here to here, or if it gains more, it can go here also. Yeah, or if the electron was here, it can go from here to here or here to here in this higher energy level. Remember, when an electron goes to higher energy level, it is excited. But after going higher energy level, okay, it also comes down after some time, after losing the energy. Okay, it does not stay here for indefinite time. Yes, if it escapes the atom, then yes, it's gone forever. But if it is within the energy level where it was, like this electron, it was here, and it basically, when it got excited, it goes to this high energy level, it will again come back. For example, this red color line over here. Okay, here the energy is losing energy. Okay, so the electron is losing energy and it is coming back. When it is coming back, that energy, okay, is emitted at this thing, photoelectric emission, like a light. You can see this in flame test. You can see these things in flame test mostly. The colors in flame test for different atoms comes because of this. First the electron is excited, then it comes down to lower energy level and it emits photons. Okay, so let's read some points from here important. okay, in its most stable or ground state, okay, the one I just showed you, stable ground state, electron could be given energy or excited and exist in less stable. If it is up, if it goes up, it is less stable and higher energy orbits. Okay, now electron could exist only certain discrete or quantized orbits. Okay, so this you're supposed to know, there are discrete energy levels. We call it the energy levels are discrete. What do you mean by that? Okay, as far as I understand, the energy levels are discrete. It means that the none of the two atoms energy levels are same. They are discrete, like they are different from each other. Like here the electron can go from here to here, or here to here, or here to here, or here to here, okay, or here to here. It can be anything, but this will not be equal to this one. Okay, because here you can go from here to here, here to here, and which is completely different from these, you know. Okay, that's what they are saying, that energy levels are distinct and they are discrete. Okay, this means that orbits have distinct fixed amount of energy. Okay, here they said, look, electron have discrete or quantized. You can ignore the word quantized. You can write electrons have discrete energy level. When an electron drops from higher energy level to a lower energy level, it gives out energy difference in the form of quantum radiation. Basically I'm talking light, photons. When electron comes back, like for example, look, if it comes from here to here, it gives you red light. From here to here, if the electron got excited, let's say the electron was here and it got excited, went up, this is less stable. After some time it comes down, it loses that energy and it gives off electromagnetic, that radiation, quantum radiation, whatever he said, photons. We can say photons also. Okay, so green color is emitted here, purple is blue color is emitted here, purple is emitted if it goes from here to here. Okay, I hope you guys understood. Okay, these are in electrovolt. If you want, you can convert them to joules. If you want, you can continue your calculation in electrovolt also. Now, so what did we learn? We learned that each atom has its discrete energy levels, and sometimes they ask you questions, why only certain wavelengths are possible? Why only certain wavelengths of light? An atom cannot give unlimited amount of lights. It gives only certain amount of light. Why? Let me take you for example. Like let's say there is an atom which has these three energy levels. Okay, so what the electron can do? Electron either can go from here to here, here to here, here to here, or that's it. These are the only three possibilities. So when these electrons come down, okay, it will emit photons, right? It will emit photons, and those photons will have different color, different frequency of light, because the energy level is different, so their frequency is going to be different. But it will be only three in this case. You think then, oh yeah, but what if we make it a 4 out of it? Even if you make a 4 out of it, it is still limited. Number you can count in your hand. Like basically here you can go from here to here, you can go from here to here, but still you can still count them. Okay, so only certain frequency is possible. Unlimited amount of frequencies is not possible, because the energy levels are discrete. Remember that. Since you have a discrete amount of energy level, you have fixed number of energy levels over here. The frequency of light that comes out, the frequency of light that comes out is also limited. You will not get unlimited amount of lights. Okay, so this actually they are going to ask you this in the examination, why only certain energy levels, a certain frequency of light is possible. The answer is straightforward. I'm going to teach you that as well, because as you can see, only certain wavelengths are possible, because only certain energy level differences are possible. You are not having unlimited amount of energy levels. No, you have finite amount of energy levels which you can count in your hand. And when you find these differences, when you see these differences, okay, you will see these numbers are limited, so it can give you only that amount of light, that frequency of light it can give you. It cannot give you unlimited frequency of light. Okay, if you have more energy level, even if you have more energy levels, still you can count them. Okay, so yeah, there when I'm going to come to the question, I'll let you know. Okay, so let's learn how to do some calculations from this thing. Let's learn how to do a calculation. Let me actually copy paste this page again, because I have to rub it. Wait, okay, let me just copy paste this page again. Okay, another thing you guys are supposed to know, the energy of the light which is emitted due to the when an electron goes from Let's say an electron goes from here till here, it goes from here, and it will emit a light, right? If it emits a light, the frequency of this light is the energy of this light is the difference in these two energy levels. Remember that. That's what they wrote here, that the frequency of the light is equivalent to, or the energy of the light, okay, or energy of the photon that is emitted is equivalent to difference of the both the energy levels, difference of both the energy levels. If you want to find this red color light, what is the energy of this light, you have to just write 3.41 minus 1.51. You can ignore this minus sign if you want to. Okay, 3.41 minus 1.41, that is the energy of the light emitted. Okay, uh, let me go to some detailed calculations as well. Okay, let's see some calculation. They said the calculation of energy in joules, so remember this, that would have to be supplied for an electron at the lowest energy level to escape from the atom. I told you, if an electron is over here and if it needs to escape, it needs to go till here. And what is the difference from the top part till the bottom part? What is the difference from the top part and bottom part is minus 13.6, but they want electrovolt, they wanted it in joules. So let me calculate this for joules for you all. Okay, so can I add an extra page over here? No, so let me do it here. 13.6 na, 13.6 electrovolt. So you should know 1 electrovolt is 1.6 into 10 raised to minus 19 joules. So therefore 13.6 electrovolt is going to be how much? To cross multiplication, 13.6 electrovolt into 1.6 into 10 raised to minus 19 joules. Do this in the calculator and see how much you get. Okay, right now I don't have a calculator with me for some reason. Okay, so how much is it we are getting? We are getting around, okay, this is what I did, 13.6 into 1.6 10 raised to minus 19 joules. It is 2.2 10 raised to minus 18 joules is there. Okay, 2.2 into 10 raised to minus 18 joules. That much energy this electron needs in its from its lowest energy level, most stable, okay, to ionize, for ionization. Now, then they said, what is the wavelength of the spectral line emitted when an electron falls from minus 1.51 to 3.41 levels? Suggest what color this line would be. Okay, so they're saying that if an electron falls from this line to this line, what will be the wavelength, right? Wavelength of it. Okay, we can find that as well. How it is done? Let me show you. Okay, so let me just take a new page over here. Page will be done. Okay, so they said from 1.51 electrovolt to 3.41 electrovolt. Let me just double check that. 3.41, yes it is. Okay, let's see what was the energy of the light emitted. Okay, so the energy of the light emitted was 3.41 electrovolt minus 1.51 electrovolt. Okay, so let me do this in calculator. So we have a calculator, so let's do 3.41 minus 1.51. How much is that? It's 1.9 electrovolt. So the energy is 1.9 electrovolt. Okay, now this is in electrovolt and we have to find the wavelength. But to find the wavelength we have to use E is equal to HF. If the frequency is in hertz, this should be in joules. So your energy should be in joules. I have to multiply this with 1.6 10 raised to minus 19 to convert it to joules. Okay, so if I do that, into answer into 1.6 10 raised to minus 19 into 10 raised to minus 19. Okay, so it's around 3.04 10 raised to minus 19. It's around 3.04 into 10 raised to minus 19 joules. Okay, so 3.04 into 10 raised to minus 19 joules is equal to H is how much is H value? By the way, 6.63 10 raised to minus 34 if I'm not wrong. So it's 6.63 10 raised to minus 34. Okay, 6.63 into 10 raised to minus 34, okay, is equal to now frequency. Now you know V is equal to F lambda. We are talking about light over here because we are talking about light. The light is, the photons are getting emitted. What is the speed of photon? Light, speed of light, and speed of light symbol is c. Remember, c is 3 into 10 to the power 8 meter per second. Okay, c is equal to F lambda, so c by lambda is equal to F. We are trying to find wavelength here, so I can write c by lambda over here. Okay, so that means lambda equals to, if I do cross multiplication of this, lambda equals to 6.63 into 10 raised to minus 34, okay, into 3 into 10 to the power 8 divided by 3.04 into 10 raised to minus 19. So we are going to do this in the calculator and see. Okay, so on how much is it? 6.63 into 10 raised to 6.63 into 10 raised to minus 34, okay, into 3 into 10 to the power 8, 3 into 10 to the power 8, 8 divided by 3.04 into 10 raised to minus 19. So the wavelength of light which we got was 6 point, if I'm not wrong, how much is it? 6.54, 6.54 10 raised to minus 7, 6.54 into 10 raised to minus 27 meter. Okay, let's see how much what was their answer. Frequency 6.54 10 raised to minus 7. Was it 7 or 27? I completely forgot. Where is the calculator? Wait, let me see the calculator. So yeah, the answer was 6.54 10 raised to minus 7, which I mistook as minus 27, whatever. So since answer is correct, it matches with our answer over here. So yeah, so it's around, okay. It's a visible, this frequency comes, this wavelength comes within the visible part of the red light. Okay, now let's try to do some other questions over here. They said between which energy level, very important questions, such questions are asked, between which energy levels must an electron fall to emit a blue line of wavelength 434 nanometer. They said it should have around the wavelength of 434 nanometer. So from which energy level should an electron go, like is it from here to here, is it from here to here, is it from here to here, or is it from here to here, is it from here to here, from where to where? If an electron falls, will it give up out an energy level of 434 nanometer? Now let's see in this 434 nanometer how much energy is there. If I could just find the energy, I can just compare with these energy levels and I can see which one matches. Like 434 nanometer they said, right? Okay, let's try to do some calculations. 434 nanometer, we already know the formula is energy is equal to hc by lambda. Hc by lambda, energy we know how much is it. H is what? 6.63 10 raised to minus 34. C is 308. And how much was the wavelength? The wavelength was, yeah, the wavelength was 434 nanometer. 434 nanometer. So wavelength was 434 nano, 10 to the power minus 9 nanometer. Do this in the calculator, you will get the energy. But this energy, what we are going to get this is in joules. Remember that. I have to convert this to electrovolt. So if you want to convert joules to electrovolt, divide 1.6 10 raised to minus 19. And if you want to convert electrovolt to joules, tahole multiply 1.6 into 10 raised to minus 19. Remember this. Okay, so if we do that on 6.63 into 10 raised to minus 34 into 10 raised to minus 34, okay, into 3 into 10 to the power 8, 3 into 10 to the power 8 divided by 434 into 10 raised to minus 9. Okay, how much is it? I'm getting an energy of 4.58 10 raised to minus 19. 4.58 10 raised to minus 19 joules. It's in joules. I have to convert, right? So I have to divide by 1.6 10 raised to minus 19 electrovolt to convert to electro 1.6 10 raised to minus 19, not electrovolt. Okay, so if I do that, divided by 1.6 10 raised to minus 19, let me give bracket. 1.6 into 10 raised to minus 19. How much is it? Sorry. It will give you around 2.86 electrovolt. Okay, let me just double check. 2.86 electrovolt. Now, which over here, what are the two things if I minus, I will get around 2.86 electrovolt. 2.86. The only thing I see is this two. I mean, that is the only differences I see. Is my answer wrong? We just got this, right? Let me just check. How much is it? How much we got in previous this thing? The difference between both of them? 1.9. We are looking for 2.86 electrovolt. Is my calculation wrong? I need to just see it. 2.86 electrovolt. Okay, just let me check over here. 2.86. Okay. 0.85 and 3.41. 0.85, 3.41 minus 0.85. Just check. That's around 2.56. So let me go much more further. 3.41 minus 0.54. 3.41 minus 0.54. 2.87. 2.87, 2.86. That means if that electron falls from this energy level to this energy level, it will give a wavelength of 434 nanometer. I hope you guys understood these calculation. Okay, so you have to write from 0.54 to 3.41 here. From 0.542 and is equal to 0.542 0.54 electrovolt to 3.41 electrovolt, or you can also write it in this manner. I think this would be way better than this. From N5 to N2. If the electron falls from N5 to N2, it gives you a wavelength of 484 nanometer. So I hope all of you understood this solution.